Performance by all these accomplished dancers here.
We're not able to hear properly.
Can you be a bit louder, please?
How am I? Am I audible now?
Not much.
Let me.
To me, you are audible. So please try to have earphones, people.
This is another test. Am I audible now?
No, not really.
Now. Can you correct?
Yes.
Much better.
This is better. Am I audible and clear?
Yes,
Much better. Much better.
Okay. So, to begin with, the title of today is Science Can Dance. And what an appropriate topic chosen by Soumya. Herself, she is Visharad and Gitanjali in Indian classical music, an exponent of dance, as all of us have just now very clearly seen. A faculty of and head of biology in DPS Raipur. So I doubt if there is any surprise that she has chosen the task of integrating science and dance, both of which are her forte. Since she is part of the troupe which shall be demonstrating various things of physics, I have been entrusted the task of running through the PowerPoint presentation. And may I request to, the actual purpose of this presentation is to demonstrate that there is science in almost all activities that we see around us, dance being no exception. And by looking at the physics that is involved behind dance, we shall be able to demonstrate the fact that the art integration effort, which has been very nicely propounded by CBSE, can be taken up seriously by the academic world, and it can be very useful in our didactic process. So without losing much time, I would request to bring up the PPT. So the title is Science Can Dance. And the objective, as already has been told by me, is to demonstrate that a performing art like dance can be used to explain and illustrate the laws of science to the learners. The roadmap for our presentation shall be as follows. Initially, we will enumerate the important dance forms of India and their constituents. Then we shall look at the observable phenomena in the dances. Also, then we shall go into the principles of physics that come in play. We'll briefly try to explain. We shall also have a look into some special moves of ballet, which have very observable phenomena of physics and are very interesting. Finally, we shall get down to our objective of seeing what are the advantages of such an integration of dance and science. Of course, at the end, we will have a short quiz to change the mood, and then any questions from the audience would be invited. So the dance forms are very well known, too well known to us: Bharatnatyam, Kathak, Kathakali, Odissi, Manipuri, Kuchipudi. And the constituents of dance that we should be observing in order to look into the physics that is behind them are balance, motion without turns, turns themselves, jumps, and transitions. The physics principles that would, in the process of studying dance, get demonstrated here would be center of gravity, the Newton's laws, especially the first law of inertia and the third law of action and reaction, law of conservation of angular momentum, law of conservation of mechanical energy, the forces that are almost perpetually present around us: gravity, friction, normal reaction, torque, velocity, and acceleration. Let's look at balance. The terms that would be coming to our notice here would be center of gravity and area of support at the floor. Also, we shall look at stable versus unstable equilibrium. What is center of gravity? Center of gravity is an imaginary point. It's a theoretical point in any body. It is there even in us, where it is presumed that the entire weight of the body is concentrated. It appears as if the weight of the body is acting through that very point. It's an imaginary point, but quite useful when we study the concepts of physics, and balance is no exception. For very symmetrical objects, as shown on the right side, their geometric center happens to be the center of gravity. For non-symmetrical objects, it has to be calculated through a due process. For any body, the action, the external forces that act on the body are gravity and the floor's normal reaction. I mean, if nothing is happening, then these two things are always acting on any body. And there is another term which we should understand for understanding balance. It is the area of support at the floor. So in this figure, we see two parts. In the left side, there is a square. In that you can see a gray patch. In the gray patch, you can see two patches representing our feet. So when we are standing equally, our weight distributed between the 2 feet, this is how our impression would appear on the ground. And then there is a gray area in between them. So if we add up all the gray area, then this entire area is the area of support at the floor. If you look at the second figure, here the person is standing on 1 foot and not too very comfortably. He's standing actually on his toe. So here the area of support, area of feet that is in contact with the floor is very less, very shrunken. So how is this relevant to the concept of balance? The concept says that a person who is standing or any object which is placed on a floor would remain static and in balance, would not topple over if the line directly falling down from his center of gravity or its center of gravity would pass through this area of support at the floor. So if the line happens to, the line vertically falling below the center of gravity happens to fall outside this area of support at the floor, the person or the object is going to fall down, is going to topple over. If you look at this dancer on the right side, you can see that the central line, the dotted line, represents the line which is passing through her center of gravity. And she is standing very precariously. It's an almost unstable equilibrium she has attained on her toe. But being a deaf dancer, she has ensured that the center of gravity is passing through that toe, that area of support at the floor, and therefore she is balanced. She may have to raise a limb, bend a leg in order to redistribute her mass so that the center of gravity is directly above that toe. Normally, a person doesn't do this very consciously or is aware that his center of gravity is at this place or he has to shift at that place. This happens like a second nature. But for a student of physics, it can be demonstrated that this second nature is achieved only because inadvertently, this is what we are trying to achieve. We are trying to achieve that our center of gravity is directly above our point of support at the floor. Now we come to the motion without turns. Here, before we come to the motion without turns, I would request the 3 performers here to show us various poses which can be used even in a class of physics to demonstrate that how balance is achieved in order to ensure that the dancer doesn't fall over, and in various difficult poses, the balance is maintained of the dancer. May I request the camera to move over to the dancers and for them to show the poses one by one. Here you can see the famous pose of Nataraja. The dancer is leaning back a bit, but her limbs have come forward in order to ensure that the center of gravity is right above her right foot on which she is standing. In this second posture, the dancer has bent her leg and raised her arms in order to ensure the similar thing. Again, the posture is very precarious. She is able to maintain on her feet only because the center of gravity is right above her foot. In this third pose, the dancer has leaned forward But this could be possible only because she has to raise her leg in order to counterbalance and bring back the center of gravity right above the foot on which she is standing, right above the area of support at the floor. So in all these three cases, thank you so much, in all these three cases, we can see that this effect could be achieved, this balance could be achieved only because the dancers ensured that their center of gravity is directly above the foot on which they were standing. Now we come to the motion without turns. Here we shall study Newton's first law, third law of motion, horizontal acceleration, how it is produced, and how this horizontal motion is brought to a stop. The first law of inertia is quite a famous one, but we shall, just for the sake of bringing everyone up to speed, a body is unwilling to change its state of rest or uniform motion unless acted upon by a force. So this is what Newton's first law is. Essentially it says every body is quite unwilling, it's quite lazy. It doesn't want to change its state of rest unless there is a force applied to it, if it is at rest. And if it is moving in a straight line in a uniform motion, then it would continue to move in that line unless there is a force that acts upon it to stop it or to enhance its speed. Inertia can be seen in both linear and rotational motions. And we can see the manifestations of inertia in our day-to-day life. Just to quote a few examples, whenever we dust a carpet by beating it with a stick, we see that the dust gets removed. What happens actually here is that the stick very forcibly moves the carpet away from its position. The dust particles, which are quite inert in the sense of unwilling, I should say, to move from their existing position, remain behind and thereby get separated from the speedily moving away carpet. And that's how the dust gets removed. Another very common example we all experience is when we board an elevator. We find that whenever this elevator starts ascending or descending, just for a split second, we feel that blood is rushing to our head or receding from our head. It's just because our body is immediately changing its position from the position of rest or from the position of uniform motion. But the circulatory system, or the blood in the circulatory system, which it takes time to cope up with that kind of movement, and therefore we feel this kind of sensation. There are many such examples which demonstrate inertia. If you have brought with you the glass, the cardboard, and the coin as requested, I would request you to place it in the fashion shown in the first figure, and place the cardboard on the top of glass and then the coin on top of cardboard. I would request you to flick away from its position the cardboard, and if you're not able to flick away as shown in the second figure, you may just hold one end of the cardboard and sweep it away horizontally from its position. Contrary to our intuition, the coin would not travel away with the cardboard. Instead, it would remain behind because of inertia, unwillingness to move along with the cardboard, and fall into the glass. So this is an example, a practical example. You can, I hope you all, those of you who have brought this three components with you would get to see this right in front of you. I would request the performers now to show us evidences of inertia in the process of dance, not only the linear inertia, but also how inertia is there even when things are rotating. So may I request the focus to go to the dancers. Here they are moving in a linear motion, and they immediately brought themselves to stop. And when they brought themselves to stop, while the legs came to halt immediately, the torso, the upper part of body, actually tended to bend forward. Can I request you to repeat this? I would request the audience to kindly look at it again with concentration. The moment they come to a stop with the immediateness. So the bending forward is actually a compulsion of the law. Thank you so much. It happened only because they abruptly brought their forward motion to a halt, but in the process, the upper part of the body refused to come to a halt immediately, and the forward bending was as a result of that. For rotational inertia, I would request them to go for the next step. You can see the lower garment. The moment they come to a stop, the garment doesn't come to a stop. It keeps whirling around and wrapping around the body. So that shows the inertia of the garment. And this is also a very nice example or evidence of inertia in dance, which, thank you. This also is a very good evidence of inertia in dance, which we can see. Now we come to motion without turns. Here, already we have learned the Newton's first law. Let's come to the Newton's third law. It's a very famous law, action-reaction law. It says, to each action there is equal and opposite reaction. And there are numerous such examples which we are aware of. First example is the shooting of a bullet from a pistol. The recoil that a pistol experiences is the reaction as a result of this firing. The second example, you can see the person who is trying to walk, the foot of the person presses against the ground or the floor in the backward direction. The frictional force as a result and as a reaction to this backward movement or backward press by the foot exerts a forward force, and this helps us to either walk forward or run or leap. Horizontal motions, horizontal movements, horizontal leaps follow the same principle everywhere. The athlete that we see here, we can see he is trying to push the ground back with the sole of his footwear, and the friction that exists between the ground helps him to move forward. We have seen examples of this in our real life also. Whenever there is a wet floor or whenever there is ice or black ice in colder places, the absence of friction doesn't allow a reactionary force to be exerted if we exert a backward force, and therefore we are not able to move forward and we fall down. So friction helps us to move forward. Similarly, whenever the dancer or any person or any vehicle has to come to a stop, it does a similar thing. It tries to exert a forward force on the ground or the floor, and the ground or the floor as a reaction following the Newton's third law exerts a backward force and helps the object or the person to come to a halt. I would request the same thing. I would request the dancers here to demonstrate this horizontal movement, the commencement because of their pressing against the floor and the stopping action because of that. You can see the footwork, and in a similar action, this has been possible only because the friction helped them move forward. And we can see the Newton's third law in action here. Thank you so much. We come to vertical jumps, something which is often seen in various dance forms. The concept that we would be learning here is law of conservation of mechanical energy. The mechanical energy we talk of consists of two kinds of energy. It can be kinetic energy or potential energy. Kinetic energy is energy possessed by a body by virtue of it being in motion. Therefore, the formula of kinetic energy is half mass multiplied by velocity square. Potential energy is the energy possessed by a body by virtue of its position relative to others, stresses within itself, electric charge, and other factors. While kinetic energy is quite visible, we can see that something is having quite a lot of energy when it is in motion. Potential energy is something a bit latent and not so easy to understand. So we're going to take some time to explain this. When we are talking about potential energy with respect to gravity, gravitational force, so the formula that is employed is mass times the gravitational acceleration constant g times the height. So higher the height, higher the potential energy. Let us make this more clear by the following example. The law of conservation of mechanical energy says that whenever in a closed system there are no dissipative forces like friction, air resistance, then the total amount of mechanical energy of that system remains constant. Now it is true that we don't have a system where friction and air resistance are totally non-existent in our world. But for our purpose, we'll presume that they are quite minimal. So what happens? How does this take place? If you see the example on the right and presume that the cyclist came from the left side of the screen at quite a speed and he pedaled fast enough just to ensure that when he stops pedaling at the foothill of this particular mound, the speed is enough to carry him with the bicycle to the top of the mount. He stops pedaling at the bottom and the speed starts dying down and he starts gaining height. When he just reaches to the top of the mount, the entire speed has died down. But what existed as kinetic energy when he was just ascending the mount actually got converted to potential energy when he was on the top of the mount. But here, the kinetic energy became quite zero because his speed was totally killed. And now, if he just rolls off on the other side of the mount, he starts losing potential energy because he starts losing height, but gaining in speed. That is, gaining kinetic energy. So again, when he's at the bottom of the mount on the other side, he's gained the same amount of kinetic energy as he had when he had just begun from the left side. This goes to demonstrate that at any point, the mechanical energy was there either in form of kinetic energy or potential energy or partly both. But whichever form it was in, their net sum, that is kinetic energy plus potential energy, remained the same. So this is the law of conservation of mechanical energy. There are more such examples. If you see this bow and arrow, in the top figure, you can see the bow has been stretched. There's no movement here. Everything is static. One would presume there is no energy. But here the entire energy has been stored by the archer in the system in form of potential energy. There's no kinetic energy, mind you. When he releases the arrow, after the arrow has left, the entire bow has come to a state of minimal potential energy, or we can assume zero potential energy. But this loss of potential energy in the bow has got transferred to the arrow in form of kinetic energy. So this is another example. One form of mechanical energy gets converted to another form, but their net total remains same. Another example is, if this boy drops this ball from a particular height, let's say from his roof, the ball, as it starts descending, it would start losing potential energy because potential energy due to gravitation was represented by mass times g times height. So as it loses height, its potential energy starts going down. But we know that its speed would start going up. Thereby, its kinetic energy would start going up. So this again is a manifestation of this law, that it had all its energy in form of potential energy in the beginning and entirely in form of kinetic energy when it reaches the ground. And its all intermediate positions, it had part of its energy in form of potential energy and partly in form of kinetic energy. But again, their net total remained the same. So one form of energy would get converted to other form, but they would remain, that their net total would remain same. I would request here the performers to kindly show the move, show the jump, which helps us to understand better how dance can also be used to demonstrate this. So here you can see that they have stored their, you see the initial position. I would request the performers to show the initial position. Their knees are bent, and by bending their knees, they have created a strain just as the strain was existing in the bow and arrow. And this strain is there in form of a spring action which is stored in their limbs, lower limbs, and this would help them convert this energy into kinetic energy when they leap up. And when they leapt up, what happened is this spring action got converted into kinetic energy. This kinetic energy took them on to a particular height. At this particular height, their entire energy was in form of potential energy. When they start coming down back on the floor, yes, when they were descending to the floor, that potential energy was converted into, thank you so much, was converted into kinetic energy again. So we see there were three conversions here. First, when their thighs were, where their legs were bent, the energy was stored in form of potential energy due to stress existing in their limbs. They released that and leapt upwards. By doing so, that potential energy got converted into kinetic energy that was having speed. This helped them gain a particular height, reach a particular height, let's say 1 or 2 feet above the ground. While they were gaining height, they were losing speed and gaining in potential energy. When they had gained that particular height, they again started descending back when their speed became 0. And again, the potential energy started converting back to kinetic energy. So there were 3 conversions here in this small demonstration. And this can be very well shown to a student of physics in any such performance. We come to turns, and the terms that we are going to see here are rotational inertia or moment of inertia, torque, angular velocity, angular momentum, and then lastly the beautiful law of conservation of angular momentum. Let us see what rotational inertia is. Rotational inertia is the counterpart of the inertia law that we read in the Newton's first law. It is actually the unwillingness that a body exhibits to having its speed of rotation altered about an axis by application of a torque. So here it says, if a body is not rotating, then it would resist if somebody starts trying to, unless it would not rotate unless there's a torque or a turning force applied to it. And if it is rotating already, then it would not change its speed or angle of rotation unless again if there is a torque. So this quantity of moment of inertia is, let us understand it conceptually. On the right side you can see a point black mass. Its mass is m, and the blue line represents the axis around which this mass is rotating. So moment of inertia of this point mass around this axis would be mass multiplied by r squared. So this point mass has contributed mr square amount of moment of inertia to the system. Now if there were an object which had plenty of such point masses, any object actually is made of plenty of numerous such point masses. So for that multiplicity system where there are more than one such point masses, the total moment of inertia would be the sum of all these contributions of mr square, as shown on the formula on the left side. But let's not go too much into these niceties, and let us understand conceptually what this thing represents. I had requested you to bring along with you a pencil and these two cloth drying clips. So for those of you who have this ready, I would request you to hold the pencil from the center and apply these clips quite close to the center. There should be just enough space in the center of the pencil for you to hold it by 2 fingers of yours like this, just as one would hold a cigarette. So you hold it like this in the center, have the 2 cloth drying clips clipped to as close as your fingers as possible. Now you try to create this kind of movement, this partial rotation. So by doing so, we are trying to rotate the system along an axis, along this axis. Try to observe the amount of effort that, notice and remember the amount of effort that is going into doing this kind of action. Now in the second step, let's loosen the clips and draw them to the fag ends of this pencil. So what I have done is, I have loosened the clips and drawn them to the farther ends of the clips. Now I would request to perform the same kind of action. I'm sure you must have observed that when the clips were drawn farther away, it is now taking you more effort to perform the same kind of action. What actually is happening is, when the mass of the body is moving farther away from the axis of rotation, the moment of inertia is going up. So it is becoming more unwilling. It is resisting any change in its state of motion, in its state of rotatory motion. So if you understand this simple correlation between the distribution of masses and the consequent moment of inertia. So if the mass is close together, concentrated close to the central axis about which the object is going to be rotated, then it is going to offer less resistance. It is going to be more amenable to any kind of rotatory effort, any kind of torque. And if the mass is drawn further away, it is going to be more resistant, and it's going to resist any kind of and this is also evident when we are riding a bicycle or a two-wheeler. If you try to balance a bicycle while it is static, it's a very difficult task. But if you start riding the bicycle and its tires are rotating, then there would be a resistance to change the state, and the body is going to be balanced. We can see this further in our next this thing. I would request, Then there is another term involved that is called torque. What is torque? Torque is as good as force, but slightly different from it. Torque represents the turning effect of the force. And just as a linear force is a push or pull, the torque is thought of as a twist to an object around a specific axis. If you look at the nut bolt here, which somebody is trying to open with this wrench, you can see that the label F is representing the force, and the length L is actually representing the distance of the force from the rotational axis. And the quantity torque here is force times this length. So if you want to increase the effectiveness, the turning effectiveness of the force you are applying, it is advisable that you apply the force farthest away from the rotational axis. We do this unknowingly daily in our daily lives when we are trying to open a door. You will always notice that the knob or the handle of the door is situated farthest from its rotatory axis, that is its hinges. You try to open or close a door by applying the same force at the center point of the door, you will find that you have to apply a higher force to attain the same kind of turning. Let's understand what angular velocity and angular momentum are. Just as we have in a linear motion, linear velocity, which we measure in meters per second, or whenever we are driving a car in a straight line, we measure it in kilometers per hour. Similarly, when something is rotated, there has to be a quantity like angular velocity to measure how fast it is rotating. And it is measured and represented by a term which looks quite close to W. It is actually the Greek omega. You can see it here. And it is measured in radians per second. That is the angle swept by that particular object around that axis per unit time. So this is how we measure angular velocity. And being a vector quantity, it also has a direction. We shall see further what the direction would be. It's a pseudo direction, but for the purpose of physics, we have to consider this quantity as having direction. Having now understood what rotational inertia is and angular velocity, let us see what angular momentum is. Now this term is very crucial. I would request you to kindly pay closer attention what it is. It is represented by the vector label L and is the product of rotational inertia, moment of inertia represented by I, and also the angular velocity. It also has a direction, the same direction as the angular velocity. And if you were to ask how would we measure for a rotating object the angular velocity, then this example would come handy. Here you can see a disk having a shaft which is rotating in the direction shown by W or omega. So in order to measure the direction of or ascertain the direction of angular momentum, a right-hand rule comes very handy. So what we do is we curl our fingers, 4 fingers except for thumb, in the direction of rotation along the axis, which also happens to be the shaft here. In such a situation, our thumb, which should be outstretched away from the wrist, that would represent the direction of not only the angular velocity but also the angular momentum. So let's not go too much into this technicality, but just to understand that angular momentum of any object which is rotating at an angular velocity of omega and having a moment of inertia of I, it would be the product of moment of inertia and angular velocity. Now we come to the crucial part, that is the law of conservation of angular momentum. The law says that whenever in a particular system there is no external torque, there is no external force or any effect which is attempting to rotate the system, in such a situation, no change of angular momentum would occur. The total angular momentum of the system would remain conserved. So just to illustrate this with this illustration, this example, you can see a figure skater in this figure. There are 2 positions. In the first position, the figure skater is having her arms stretched outwards. And if you can notice, she has her right foot also bent, right leg also bent, thereby that is also separated away from her central axis. What is happening because of this, as I've already demonstrated with this clip and pencil example, that her moment of inertia has gone up. She has a very large rotational inertia. And she has a particular rotational speed which she has acquired by turning herself. In the second step, deliberately the dancer brings her arms closer to her body and also her leg closer to her body. By the same rule, she has actually brought down, she has maneuvered her limbs in such a way that her rotational inertia has come down. Now, since the law says that the product of rotational inertia and the rotational velocity has to remain same, Therefore, her attempt to reduce her own rotational inertia would be accompanied with an automatic increase of her rotational speed, rotational velocity. So you can see that in the figure it is represented that she would start spinning much faster the moment she brings her arms close to herself. And this would happen without her making any extra effort for this. It would happen automatically in compliance of this beautiful law of conservation of angular momentum. And let us try to see a video which would demonstrate this very effect.
Skaters must
Here
learn
the
to
ice skater
understand and use angular momentum
has
to become the best in their
acquired
sport.
initial
Angular momentum is the product of a skater's
rotation
moment of inertia and angular velocity and is represented by the letter L. When
The
the,
moment of
skater is
inertia
rotating with no net external torque acting on her, angular momentum is conserved.
and omega
With her arms
together
and leg
multiplied
outward, she increases her moment of
create L.
inertia, which
Here her
reduces her
arms are
angular
farther,
velocity.
eye is higher.
As she
The
pulls her
moment she
arms and
closes
leg
them in,
inward, she
she
is able
started
to spin
spinning faster,
since her angular
and her omega
velocity
is going up,
increases
and
while her
eye is
moment
going
of
down.
inertia decreases. And this is how skaters become champions.
While this was evident in this beautiful piece of ballet, our
Skaters
Indian
must
dances
learn
are
to
no exception, and I would request our performer to demonstrate this in Indian dance form. She has taken an initial rotation with the help of her feet by giving torque on the floor. Her limbs are outstretched, and as she is closing in the limbs, her speed is going up. It is easier for her to rotate when with her limbs drawn inwards. Thank you so much. Now we come to some observing some special moves in ballet. They are tongue twisters. One is fouette and the other is grand jeté. Let us see what these dance moves are, and then we'll discuss the physics behind them. So let us see what a fouette looks like. Notice the video, and she is able to make multiple turns, and it appears as to how did she get the torque, how could she move continuously. And now let us see the physics behind fouette through this
The
explanation.
dancer starts the fouette by pushing off with her foot to generate torque, but the hard part is maintaining the rotation. As she turns, friction between her point shoe and the floor, and somewhat between her body and the air, reduces her momentum. So how does she keep turning? Between each turn, the dancer pauses for a split second and faces the audience. Her supporting foot flattens and then twists as it rises back onto point, pushing against the floor to generate a tiny amount of new torque. At the same time, her arms sweep open to help her keep her balance. The turns are most effective if her center of gravity stays constant, and a skilled dancer will be able to keep her turning axis vertical. The extended arms and torque-generating foot both help drive the fouette, but the real secret, and the reason you hardly notice the pause, is that her other leg never stops moving. During her momentary pause, the dancer's elevated leg straightens and moves from the front to the side before it folds back into her knee. By staying in motion, that leg is storing some of the momentum of the turn. When the leg comes back in towards the body, that stored momentum gets transferred back to the dancer's body, propelling her around as she rises back onto point. As the ballerina extends and retracts her leg with each turn, momentum travels back and forth between leg and body, keeping her in motion. A really good ballerina can get more than one turn out of every leg extension in one of two ways. First, she can extend her leg sooner. The longer the leg is extended, the more momentum it stores, and the more momentum it can return to the body when it's pulled back in. More angular momentum means she can make more turns before needing to replenish what was lost to friction. The other option is for the dancer to bring her arms or leg in closer to her body once she returns to point. Why does this work? Like every other turn in ballet, the fouette is governed by angular momentum, which is equal to the dancer's angular velocity times her rotational inertia. And except for what's lost to friction, that angular momentum has to stay constant while the dancer is on point. That's called conservation of angular momentum. Now, rotational inertia can be thought of as a body's resistance to rotational motion. It increases when more mass is distributed further from the axis of rotation and decreases when the mass is distributed closer to the axis of rotation. So as she brings her arms closer to her body, her rotational inertia shrinks. In order to conserve angular momentum, her angular velocity, the speed of her turn, has to increase, allowing the same amount of stored momentum to carry her through multiple turns. You've probably seen ice skaters do the same thing, spinning faster and faster by drawing in their arms and legs.
So I think it is quite clear from this explanatory video as to how this beautiful and seemingly difficult move of dance, fouette, was accomplished by this dancer. And if we try to look at it again and summarize again, she is gaining torque from her first move, and then when she is outstretching her leg and limbs, she is gaining balance, and by closing them, she is gaining speed, and after having turned once, she brings her feet back to the flat position, gains torque again, regains her balance, and then she is back on her toe again to accomplish the rest of the rotation. Again, now let us see this second very beautiful move in ballet called grand jeté. If you look at the dancers, they would take a run up, then take a leap in the air. And what is beautiful about this leap, it appears as if they are floating horizontally during this leap, and then coming back to the ground. The audience is spellbound as to how this floating effect was accomplished by these dancers. Is it magic or something? It's not at all magic, it's pure sheer physics. And let us see the physics behind this. Why do these dancers appear to be floating? Let me show you the video again so that you can appreciate it better. They take a run up to gain speed, take a leap in the air. And while they are in the air, they stretch their legs in the fashion, in a total horizontal manner, and then descend back on the floor, bringing the legs together again. So how does this come about? Normally, if you leap in the air, or if you throw an object in the air, we expect
Sir, we
the
lost your
movement to
voice.
be natural. If it passes, if it follows a curved trajectory, a projectile path, we say often.
Yeah, so your voice, we lost your voice, sir.
Okay. Am I audible? Am I audible? Call up somebody. Am I audible? Okay, no response. Am I audible? Can somebody, any of the audience, from the audience? Can you hear me? Can anybody respond by through a message? Am I audible?
Yes, now, yes.
Okay, okay. So what was the last slide till which I was audible?
Before this slide, I mean, just the moment the video ended, you were audible till then when you started this one.
The Grand Jetty?
We could, yeah, the explanation of the.
Or the Fouette? Was the Fouette complete? Okay. Let me begin with Grand Jetty again. So let us see this video, and this is a very beautiful move. The dancers take a run up, the leap in the air, and during the leap, they totally stretch their two legs in a horizontal position. It appears as if they are floating in the air, and then they come back on the ground, bring their legs together back again. Why does this floating effect appear to us? And what makes it happen? Let us see the physics behind it. Normally, whenever something is launched in air, thrown in air, for example, a stone in this case, we think it has followed a natural path if it has followed a curved path like this, as shown in the figure. This path is parabolic in shape, and it is called projectile path. Not to go into the nitties and gritties of this, even if we take a leap in the air, a high jumper or a long jumper, it appears natural to us only because he follows a curved path, a projectile path. But what the dancers are able to accomplish here, that whenever they are jumping, they are taking the leap, it appears that they are moving in a horizontal direction, as if they are floating on water. What they do actually is, the moment they have leapt in air, they stretch their feet to the maximum. By doing so, they have raised the center of gravity to a higher level. Now, the parabolic path compulsion holds true for everything, including this dancer and including the dancers performing Grand Jetty. But the catch is that it holds true for the center of gravity. So the center of gravity should follow this curved path. The trick that the dancers are creating here is that they are midway in the mid-air, they are relocating their center of gravity. So by raising their center of gravity, they are able to descend a bit and letting the center of gravity follow the law. But the visual that is presented before the audience is a different thing. If you look at the center of gravity, at either end, it was somewhere near the waist of the dancer, near the pelvic bone, but mid-air, the dancer has managed to relocate the center of gravity by raising her legs to somewhere close to her chest. By doing so, her head doesn't need to traverse that curved path, and instead, whenever we are in the audience and we are looking at the dancer, we are normally looking in the eyes or the face of the dancer. And the dancer's face, you can see, is all along in a straight line. And we presume that the dancer has actually floated in the air. So this effect could be accomplished because the person who might have invented this was good at physics and would have very well crafted this kind of move to create this magical special effect. We come finally to the significance of such an analysis of dance by understanding the physics behind it. First and foremost, the objective of this presentation is very well accomplished, where the physics behind dance, if it is told and demonstrated before an audience which consists of students, learners, then it becomes education for them. The concepts become very well ingrained and etched in their minds. It becomes a fun way of learning. They understand it better, they remember it for a longer time, and they develop a tendency to look for science in not only dance, but in their every walk of life, every activity that is going around them. It develops a scientific temper in them. The audience also, if it has a better knowledge of physics behind the dance moves, it is able to better appreciate the moves, the transitions, the poses, and the aesthetics. There is a certain enhancement in the level of appreciation if you happen to know the physics behind it. And then such an analysis and such a knowledge is also good for the dancer and the dance instructor. Very few might be aware that dancers are also quite prone to injuries. They also make a lot of effort to master many moves and many kinds of steps, many kinds of poses. So, and it quite varies from body type to body type. So if they know the physics behind the dance, they would be in a better position to understand their limitations, in a better position to avoid injuries, in a better position to accomplish various dance moves and various dance steps. So let us come down to quiz. If you are all ready for it. तो सबको अनम्यूट करना पड़ेगा क्या? So if you are all ready for a very short quiz, just to change the mood from a monologue to a two-way participation. Can I begin? So let us see this figure in front of us. We can see that a person is holding a wrench to open a car wheel nut. The very simple question before you is, there are two car wheel wrenches here. One is having an arm length of 50 centimeter, other is a shorter one in B, 35 centimeter. So the question is, which wrench would be more easy to use in removing car wheel nut? Which would afford you more ease? Which one would you choose? I would request you to kindly enter your answer in the chat. I see all the correct answers. And if you could also, somebody could type in the actual reason why would it be so. Why is A preferable? Why is A preferred? Great. Monica Sindhwani has written greater torque. Exactly. Torque is greater, correct. So let us, from wherever we are sitting, a round of applause for all the people who have given the correct answer, and not only the correct answer, the correct reason as well. The longer arm length is the L that we showed in that diagram, and that creates a bigger turning effect. So whenever any person who has had the misfortune of a flat tire would know this very easily. The question 2 is, before coming to the question 2, I would request the performers to give a demonstration of a pose here. So this is a Nataraja pose, and the famous Nataraj pose. Thank you so much. Let's show the question. So which concept of physics does this pose best demonstrate? First is frictional force, conservation of mechanical energy, center of gravity, and torque. Everybody is saying, see, so a lot of winners here. It seems the concepts have been understood very well, center of gravity. So again, a round of applause for all the winners, all the persons who have answered it correctly. We'll come to the question number 3. You can see the headrests that exist in a car. And the question with respect to this headrest is the top portion of the seats. Let us see why are they useful. The first option is, it is useful for protecting the occupant or the driver of the car from a head-on collision. So the car has hit a wall in front of it, and this headrest is going to protect him from that. The second option is to maintain a correct spine posture. The third option is to keep the driver alert. And the fourth answer is to protect from a rear end collision. So the driver in question here is the girl in the blue car, and she's having a headrest behind her, and there's another car which has hit this car from behind. So let me ask, which Purnima Ravi has said D? Everybody is saying D. I think these are all science teachers. And if you could also write down the principle of physics, because equal reaction, I doubt if this is the right reason. Third law is not the right reason. Inertia is the right reason. Monica Sidwani, inertia, yes. The first law is the reason, and therefore D is the correct answer. We come to the question number 4. You can see the driver of this car is trying to change the direction of car using the steering of the car. So which concept of physics is best highlighted here? One is rotational inertia, B is conservation of energy, C is torque, and D is angular speed. Let us have the answers. Ayappa Raj has said C. A is not the correct answer. C is the correct answer. Again, to all those who have answered correctly, this is a force couple that is being applied on the steering. We do it daily when we are opening the tap. We are applying a force couple. We do it daily when we are turning the steering of a car. And again, the law that is the physics term that is applicable here is torque. For question number 5, I would request the camera to focus on the stage, and then we shall see a dance move, and then
धन्य भाग सेवा का अवसर पाया, धन्य भाग सेवा का अवसर पाया पाया, धन्य भाग सेवा का अवसर पाया पाया, धन्य भाग सेवा का अवसर पाया, चरण कमल की धूल बना मैं, चरण कमल की धूल बना मैं, मोक्ष द्वार तक आया, धन्य भाग सेवा का अवसर पाया पाया, धन्य भाग सेवा का अवसर पाया।
spectacular, spectacular. Thank you so much, all the performers. What a beautiful way of concluding this with a question. The song sequence in this was a Thanksgiving song. And the question comes here is, if you would have noticed the jump in this dance move, then which principle of physics does this upward leap, upward jump? It is torque, Newton's law of inertia. Kindly read the third option as law of conservation of mechanical energy, and D is center of mass. Kindly read the option C as law of conservation of mechanical energy. I think all are mentioning it C. Therefore, almost everybody has got it right. Thank you so much. And a round of applause for all those who answered this correctly. I would now request, open the floor for any questions. If there are any questions with regard to the points that have been discussed.
So, good evening. It was really wonderful to witness this spectacular, interviewing dance with physics. And especially, when you were talking about that jump, I was thinking of a high jump that those athletes do. That normally, when they first run, I think so how would we explain that when they do a high jump, they try to cover that horizontal bar, their weight.
Even there we can see evidences of physics. A very good example, I would take it further from there. You can, if you see a pole vault, a person,
Yes.
person runs with a very flexible pole, and just as he has to commence his upward movement, he fixates that pole on the particular point in the ground. And the bend that is created is because of his kinetic energy getting converted into that strain energy into the pole vault. It starts bending. There's a spring action, there is a strain in it. And when that pole starts straightening up, it raises the jumper. And by raising him, the strain energy in the pole starts going down, and he starts going up in his potential energy. And when he's at the top point, his potential energy is again at the highest, and when he leaps on the other side, he comes down on that foamy thing, he has gained a lot of kinetic energy and his potential energy. So a lot of conversions involved in the process. In a long jump also, this is true, but yes, in a high jump, this is very much true. Since the jumps in dance have to be quite aesthetic, we would not expect that height to be too much. So
Yes.
probably a slow motion video would be a better video to show at leisure the various conversions while you're also describing them verbally.
Thank you so much. Thank
I
you.
have a question, Soumya dear. Pranam to you and your team and to Sir too. And I want to ask if this was a magnum of preparation, why didn't we make it YouTube live? Thousands would have watched. We would have advertised it. And I'm hopeful. Thank you for recording. And I really, really am pleading to you that just one or two parts where we were quipping in, complaining about sound or something, removing that, I would request you to kindly make it into a complete video, which should be on YouTube. And you have no idea, the science faculty of the professors and colleges, they struggle hard to bring home certain concepts to children who are coming from class 12th also.
Yes.
And the entire Shakti Vibha wing of Vigyanika, if you're aware of it, they would literally take it on a platter as a resource for the college students, for the higher education students. And this is such a beautiful presentation, meticulously made. How you've trimmed it and brought in everything. I mean, pirouette, forte, and Bharatnatyam, Kathak. I think today it was Safit. We've had the dessert of all possible flavors, I would say. So pranam to you, and I'm really, really very thankful for you to chisel out such a beautiful presentation. And please, please allow us to share this with all our students,
Yes, ma'am.
if you do that.
Thank you so much, ma'am.
Thank
Thank you for your
you.
kind words, ma'am. Thank you.
Soumya and the team, I really second every word that Sunita has said. Believe you me, I can't say I am a dancer, but yes, a pretty moderate one till even after school and in college. But believe me, even though I'm from science background, I could never correlate the simple dance moves to such scientific concepts. It was an eye opener. An eye opener, in spite of me being from science and being a dancer. This was an eye opener, and I would just say that hats off to the whole team for putting it together. The amount of coordination and preparation is so very visible. But then I'll just say one more thing. Ye dil mange more. Pardon me for being greedy, but do you still have a few examples from chemistry or biology?
Yes, ma'am.
We would love to hear it. Thank you so much once again.
Thank you so much.
I can already see Soumya showing germination in her graceful dance moves. I can imagine it so easily. And Geeta ma'am, absolutely right. I'm not from science stream. I'm completely from arts, but a music lover, hopeless arts lover. But this is such a beautiful treat for the eyes and for the mind. And I understood so many physics concepts today through dance. Yes, over to you, Soumya. Thank you.
Thank you so much, ma'am, for having faith. Thank you for being the support you all are. Kind and thoughtful, sensitive and considerate, a generous and thoughtful giver. You are all unselfish, always putting others before yourself, making us feel special and important. It's a privilege and a pleasure to be associated with such illuminaries, BCSAs. Thank you so much. Thank you.
Thank you, Soumya. I don't know how to express everything that Sunita has said, Geeta has said, but I don't know what to add to it, but it was splendid. It was really, really, really amazing.
Thank you. Last but not the least, thank you, Arijit, for giving me this opportunity to showcase the integration.
Thank you so much, Soumya. This was such a fantastic and spellbound. I'm absolutely spellbound. I just don't have any words. Thank you so much.
Start our own YouTube channel and let this be the first entry, because things are happening at such stature here. I think there are many people who will be learning, gaining from the kind of presentations which are being made. Not that everything has to go there, but I mean the stature of this presentation, we are all awestruck, and absolutely this needs to be spread like sunshine out into the world. So if you all agree, we can have our own YouTube channel now. Yeah. Dil mange more, ma'am said no, so I'm just translating that into action.
Thank you so much. Thank you, everybody. Thank you.
Thank you. Thank you.
Thank you. Thank you all.
Bye.
Thank you, everyone. And thanks, Arijit, for coordinating.
Thank you. Thank you.
Thank you. Thank you, Soumya ma'am. Thank you so much. Very well coordinated. Thank you. It's awesome. Thank you. Thank you. God bless you all. The whole team, I can say.